sort of like a sandbox example of campus awareness of sustainability issues and what an exploratory version of that research might be, maybe a descriptive version, and then starting to get into an explanatory version of that, and with each of those getting more sort of narrow and specific, because explanatory research, in order to be able to test and break mechanisms and test and break theories through breaking hypotheses, rejecting hypotheses in statistical language, it has to be sort of laser focused on that specific little part of the bigger phenomenon. So exploratory research, big wide angle lens. Explanatory research, kind of an electron microscope, narrow or laser focus. So that's cool. That's exciting. You get to do different kinds of things at different stages of a research project when you're looking at something from kind of its whole life cycle. So for explanatory research, again, we want to test mechanisms. We want to try and identify and test for and against causality. So if we think that, based on our descriptive research, factor A is correlated with, or proportional to, or inversely proportional to, negatively correlated with, all kind of the same idea. If our descriptive research says there's some relationship between these two, and there is some other relationship between C and factor B, and not really any relationship of factor D to factor B, then we sort of step forward into explanatory research of, okay, so A is strongly correlated with B, C is less strongly correlated with B. Is this an A causes B situation? And C can cause B situation, but not as well as A. Does C need to work only in the presence of A? So it is a contributory factor, and this is a necessary factor, and this potentiates or upregulates or downregulates the expression of B, or dependent variable, or outcome. So you can get into some pretty cool stuff, but everything has to be deeply, fundamentally controlled as much as possible, and that's hard to do in field studies for a lot of reasons. Not least among those weather, but also things like if the formulation of glyphosate that the farmers are using on some of your fields changes year on year in a longitudinal or a time series study, maybe this 2023 version of glyphosate interacts with water, rainwater, just a little bit differently than the 2022 version did. Some of the farmers are using up their old 2022 stuff, some are using 2023 stuff. You're measuring water samples at both and seeing some difference there. The question is that difference because of some possibly unknown factor like what the farmers are doing? We're going to collect those all together, all those unknown factors, into an error term in your statistical model. And what proportion of the behavior you're seeing in your outcome variable, these attributes of these water samples that you collect maybe, ideally your experiment is manipulating most of the effects and able to cancel out or negate or obviate any of the other possible factors. But sometimes the farmers don't think to tell you, oh, I'm just using up last year's formulation, and maybe the other farmer doesn't say anything about, I'm using the 2023 version or whatever. You just have to sort of know all that stuff. So it involves a lot of controlling, a lot of communication, a lot of contact with research participants and design, and just hard work to account for everything that you possibly can. So we'll skip through another example here. For causality, we need a couple of things. To figure out the arrangement of these arrows between input and output factors, we need a couple of specifics that we've alluded to, but we'll sort of get into a little bit more detail with it. So first and foremost, there has to be association. there needs to be some correlation, we would use this as a statistical term, between factor A, the upstream factor, the input factor, the independent variable, and B, the downstream factor, the dependent variable, the output or outcome factor. There also needs to be sort of obviously basic temporal order, and as obvious as it is, we need to make sure to include this every once in a while. We get so close to thinking about a research project, it's like, oh, these factors are happening simultaneously. One can't cause the other because they're happening simultaneously. In a complex systems, you have a lot of simultaneous factors, so one has to be upstream of or before in time the downstream factor in order to influence it. So we would call that temporal order. Spatial order might be another way to think about temporal order. Like when you're dealing with watershed studies, necessarily, unless something weird is going on like a pump system, you have to consider what's happening upslope before you consider what's happening downslope, because upslope is affecting downslope, and downslope, you could assume that downslope is not affecting what's happening upslope, except in some cases that's not necessarily true with capillary action, wicking, transpiration, pumps, stuff like that, moving water the opposite direction of what you're assuming it would flow. So temporal order also means spatial order, but it's just a sense of A has to come before in the watershed or in time and space B in order to be able to affect B. Finally, we need to discard or reject or falsify or break alternative or competing factors. So these are things that you are holding constant in your experiment. These are things that you are not able to hold constant like weather, but you're statistically applying a blocking effect. You negate the effect of a little bit more rain on this watershed than on that watershed. Usually paired watersheds are right next to each other to not negate the effect of rain, but to hold equal across those two adjacent watersheds the approximate amount of rain that each one got. Now they didn't get exactly the same amount, but we'll hold it as close as possible, right? There's just gonna be a little bit more rain or a little bit less rain on one or the other, and so forth. So among these, we want to identify and work really hard around confounding factors. So a confounding factor is something that you think isn't really affecting the issue at hand, and so it's not well controlled in your experiment, but it is. It's confounded. It is found with your actual factors, okay? Spurious factors are sort of the inverse. A spurious factor is one that you think is affecting the system and it's not actually. So you pay too much statistical attention to spurious factors when they're not identified way upstream and essentially removed or negated from the study. So there's a lot of specifics in each of these three big boxes that individual stats and fields methods classes will get after, but the basic sense is your research study probably has a lot of work baked in on, did we do a whole bunch of descriptive research to figure out, yeah, A is correlated with B, or is negatively correlated with B, and that's a robust correlation. We see that across lots of different study sites. We see it across a lot of similar but not identical ecosystems relative to the one that we are working in, and so on and so forth. Temporal order, fairly straightforward, but every once in a while people just lose track in a complex mechanism, realize or fail to realize that things are not happening A then B, it's just A, B together at the same time and dynamically influencing each other back and forth, and that's real muddy statistically and hard to piece out. So, alternative and competing factors, Usually, for the most part, you have a fairly clear sense of what those alternatives might be, but the fundamental point of setting up your hypotheses, making your research question very specifically worded, is really getting after this disproof of alternatives and failing to disprove the alternative that is the real thing, the legit, actual alternative hypothesis. So, for this, let's say, describe to me a field study in your area of study, and we'll come up with a couple of hypotheses around the null idea, that there is no effect or meaningful interaction. An alternative hypothesis that yes, factor A drives factor B, and might be mediated or moderated or influenced by factor C along the way. And then maybe a spurious factor. So that is a hypothesis that we want to fall apart. So we stick that as spurious factor D influences, our hypothesis is that spurious factor D influences our outcome variable V. And our research shows that no, factor D does not drive the behavior of factor B. So we reject that hypothesis. That's a victory. It takes a little bit of weird brain wrapping around this idea of we're trying to falsify, we're trying to nullify, we're trying to disprove hypotheses instead of trying to prove them. If something works, we don't know why it worked. If we manage to break something intentionally, we know how we broke it. And that is how we get at, how we kind of back into how something actually works. It's sort of weird how that goes, but that's kind of the fundamental understanding of how statistics work and help us to not prove things, but disprove alternatives. Okay? We rule things out until there's only one possibility left. So, for field hydrology study, what might be a basic A-B relationship, kind of a study? X influences Y, or drives Y.
Fertilizer put on fields increases the amount of nitrate that runs into watersheds. Maybe. I guess is a good way to word it.
Alright, so increase in the presence of fertilizer, applying it, is forward proportional or positively proportional to nitrate species, nitrate, nitrite, nitrous, etc. Free nitrogen, those increase as well. Okay, cool, awesome. So, in our sort of basic letter schematic system, we've got A and we've got B. What might be a spurious factor D that we hypothesize increases nitrate, nitrogen, nitrite species concentrations down watershed, downstream? What might be some other thing that, you know, on the face of it could drive this, but secretly you and I know that it doesn't, because we're expert researchers in watersheds. DMV or BMV offices nearby proportional to observed increases in nitrogen species concentrations observed downstream. So we could say this. This is a thing, right? So DMVs have a lot of MVs nearby. And MV is ICEs, their internal combustion engines, run hot enough to crack diatomic nitrogen and put out a whole bunch of NOx compounds. This is one of the primary components of smog. So, we We can hose the area down with a whole bunch of synthetic fertilizers, and or we could have a whole bunch of vehicles nearby. But we measure this out and we realize, okay, yeah, there's a whole bunch of this vehicular activity right next to this field, and we're measuring a whole bunch of increased nitrate, nitrite, etc. But all of the NOx compounds in here are gas phase, and they're just going away and diluting so rapidly with the fourth power of radius against concentration. Excuse me. That there's just no measurable. We get down into the parts per billion range in terms of condensing gaseous nitro compounds. It's 1,000 to 1 reduction in volume. So, yeah, at the tailpipe, we are generating like millions of tons of nitrogen species as smog, but not a lot of that is going into this watershed where we're measuring. So we measure that stuff out. We test a bunch of fields where we're not applying fertilizer and where we are applying very known and strict amounts of fertilizer, and we are maybe measuring both sets of fields, and we're able to rule out this spurious factor. And we can't rule out that fertilizer influences nitrate because we did see big increases in nitrogen species where we applied fertilizer and so forth. Okay. So a confounding factor is one where we think it might not, or we suspect or hypothesize that it might not affect our dependent variable, but it does. Our model is too simple. It should include that factor, but it doesn't. So in our example here, what might be something that does legit add nitrate, nitrite, or whatever into downstream measurements or downslope measurements, but that is not fertilizer? Something that we really should keep track of, but maybe in a poorly designed experiment, let's say we wouldn't. You guys would never fail to grapple with confounding factors. But let's say some careless jackwagon of a researcher was out there doing some pretty cowpoke research and just completely ignored something that was pretty important. So what might be some other actual sources of nitrogen species that could confound our study if we're just interested in studying this? And we need to account for those.
Like dump sites.
Okay, awesome. Let's see, so animal, ag, slag pools, dump sites. Both of these can be, under specific conditions, proportional to X compounds increased in observation downslope downstream. Okay, so we need to take a wider look on our map and figure out, okay, so for 2 out of the 65 field sites that we are measuring this stuff, 2 of those are downslope from production animal agriculture, CAFOs, animal feeding operations, or something like that, where there's a whole bunch of manure getting generated. And every once in a while there's a storm and the sewage retention ponds break and release millions of gallons of feces into local waterways, across fields, what have you, and so forth. So we need to track this and keep kind of an earmark on those 2 particular sites and ask ourselves in the statistics when we finish it out, do we have any storms that caused any spurious leakages? And if so, what do we do with those 2 fields out of the 60 or so different field sites we've been monitoring for 2 years or whatever? Do we throw those data out? Because there's just no way for us to disentangle with 2 sites the specific proportion of influence of that animal ag, the sewage slag overflow, or the complex fractured subsurface flow of leachate from a dump site flowing sideways and maybe hyporheic charging nitrate species or nitrogen species upward into the bottom of a farm field. maybe it's just too complex, and we say, you know what? If we throw these two sites out, we eliminate this confounding factor because all of our other fields are at the top of their watershed. There is nothing else upslope from them. So it's pretty clean in terms of inputs. Just the stuff that we are putting in a controlled fashion with different treatment levels, different timings, whatever, of fertilizer, that's getting us a clear and clean proportional downslope output. Sometimes we just throw these out. Sometimes we can't throw these out. Sometimes we don't want to throw these out because we think this might not be a confounding factor. This might be another important, like, first-class citizen factor that we really are interested in, and we want to track it and understand. You know, maybe we've already done some studies where we have a pretty clear sense of what this fertilizer and nitrogen species relationship is. Now we want to know how it can go wrong in the real world, where sometimes, like, the dam that holds the shit gets fucked. That was a lot of curse words in one sentence. Pretty proud of that. Anyway, no, that's terrible. So sometimes a confounding factor is a real problem. If we don't know that this exists and it's happening, that is the classic confounding factor situation. Like, reality is more complex than your experimental model, and it's causing weirdness in your data and running up the variance in unexplained ways. So that's confounding. When you pull the confounding factor or factors into the study and turn them into actual either experimental factors that you're controlling or blocking factors that you are statistically neutralizing, so to speak, then it's no longer a confounding factor, it's just part of your model. And you are on a statistical level instead of a logistics level, at the back end instead of the front end, including or excluding or weighting the effect or influence of these things, figuring out what that effect or influence or weight is. Okay, cool. So we have main factors, we have spurious factors in this example, and we have either confounding, which is bad, or additional main factors or blocking factors, depending on how we treat it statistically. And really the question that you're asking, fundamentally, is deciding whether animal ag slag polluting your farm fields, either overland flow or hyporeic charge or whatever, your research question kind of sets whether you're going to treat that as a confounding factor and maybe throw those out because you're trying to isolate away, negate, get rid of those effects, or treat it as a blocking factor of, yeah, we're going to roll this right into the study and we're going to keep sampling those two sites and see what interesting data we get there. Maybe you get so much data quantitatively that you can, maybe it's not 2 sites, maybe 20 out of 60 sites have this set up. And so a third of your sites, well, now we can run some stats on a third versus the other 2/3. You know, we can get some interesting stuff out of that and, you know, maybe produce some new statistical insights that just looking at fertilizer, maybe that is an incomplete model for practical use in the real world. Okay? So, there's a lot to be done in good ways with this. Is this pretty clear so far?
So, like, if you were to have a confounding factor, and say if it was just like 1 side or 2 sides, and it's just like really skewing a lot of your stuff, would it be possible to say, like, should we just get like rid of this site? Like,
absolutely.
just completely get rid of it, or like, I don't remember. I forgot what I was gonna say for the other part, but yeah. So you could just like completely get rid of an entire site if you just think that it, or see that it's completely messing something up.
Yeah.
Statistically wise.
Yeah. So yeah, and again, that getting rid of that site can happen at a logistics, like a research, design, and planning phase, or it can happen sort of post hoc. That is, after the fact of we've collected data, including on these sites that might be confounding or maybe like broken in some way or poorly controlled. if you want to think about it, like you're probably for this fertilizer study doing all of your work on soy fields or wheat fields or barley fields. Like if you're mixing the crop as well as the fertilizer application and so forth, that's an extra layer you got to keep track of. Which species is getting grown on here and so forth. And they have different timings and like when you plant them and stuff like that, and how long they need to grow and so forth. So it's way simpler and clearer to get that sense of what is the fertilizer doing with nitrogen species by eliminating like all of the soy fields so we can just focus on wheat. That's a front end way to do it. At the back end, it very, very commonly shows up as, oh man, I'm having these fond and homesick dreams of Hawaii while I'm crunching statistical data at 2 a.m. in the ag building, and we're in the bullpen or whatever. And everything was going fine until about midnight when I started analyzing the data sets that included these animal ag fields up watershed of where I'm working. And none of my statistical tests are working. Like everything was fine before I started rolling those in. Or so in that case, you start having this conversation with your advisor of, look, everything's great on like 58 out of these 60 fields, and on these 2 fields, nothing worked. Can we just, we did all the work, we collected all the data for those fields. Can we just drop those from our data table and keep on going with the 58 fields, which is pretty good? That's like 96, 97% of our fields made it all the way through. I'm pretty proud of that. We can get good work done with 97% of our field sites accounted for. And, in your methods, it's very common to have a one-sentence thing of, in post-hoc analysis, we decided to drop 2% of our field sites for uncontrollable cross-contamination purposes or something like that. Very, very normal. In survey research, it's normal to get, so for every 100 people that we ask or approach, let's say 95% of those consent to take the survey. So we're down to 95% of the original pool. And of those 95% of those make it to the last page of the survey. And of that 95% of 95% of those, so now we're down to about 90% total, correctly filled out all the questions. And so, yeah, we're only dealing with 90% of the 100% that we totally started with, but that's not the end of the world. Like, if somebody was legitimately unable to complete the survey because maybe they've already completed it once, is a very common way for somebody to get ruled out. If they filled out that survey again, there's a test retaking effect in surveys that completely destroys the validity of that particular survey response set. So it's not an embarrassing thing to have to remove those. It's like, no, in order to be responsible and ethical in representing these data as everybody took this survey the first time, we have to throw that person out. And we really appreciate them helping out with the survey, but we just can't ethically use that data. So it's not at all a problem to discover a confounding factor. Now, sometimes with a larger study, maybe in a quarter of your sites, you find something like that, and you're not sure what that reason is. You only even become aware of the confounding factor in the statistical analysis. Like, maybe you've done some of these studies before, you have a pretty good sense of how the stats should be coming out, and they're just not. Like, you did a good study, your data are good, but there's something else going on. That's the really exciting part. So a lot of the quantum leaps in various different fields of forestry and field ag and chemistry and physics, a lot of those don't happen with a regular study that turns out exactly as you expected it to, because you did a great literature search of previous work that's similar. You have a real good sense of where your study is going, you do it well, everything comes out beautifully. That's mostly an unremarkable study. It's like, yeah, okay, great work. Everything worked out, and we confirmed what we expected. That's fine. When you find some latent confounding factor, latent meaning not explicit, and you have the data set and size and well-controlled experiment to split out those 20 sites out of the 60 total and compare them against the others and figure out what that confounding factor is that nobody's looked at before, that's really exciting. That's one of the quantum leap moments where like a huge proportion of Nobel Prize winners had that moment of not, okay, everything turned out exactly as I wanted it to, let's publish it, let's ship it, we're done. They're working late into the night and they're looking at the stats and they're like, that's weird. Like 95% of this is totally by the book and 5% of it is consistently weird. That's not random error. There's something going on. All right, let's drill down on that 5%. Yeah, we'll finish out the regular study and publish all that. That's fine, whatever. But this is how we learn that CAFO operations totally destroy downstream sites or down watershed sites by nitrification, eutrophication, and stuff like that. Like it's a statistical bycatch. We're fishing for salmon and we got a dolphin. And dolphins are really cool and interesting, but we weren't looking for that initially, but we found a dolphin. That's cool. Now, bycatch is a super bad problem. Save the dolphins. But yeah, so a lot of interesting science happens not from, whew, I'm done. It's, that's weird. I didn't expect that. Because by the time you've done your literature review, generally speaking, 90% of what's going on at your study site before you ever step foot on the field site. All right, so that's a lot of bloviating about that. Let's move on from testing for causality. So we'll go through a couple of examples of real-world causality studies where science was abused or science ran aground of some of those things we talked about at the very beginning of the semester, or at the beginning of this part of the semester, talking about things like premature closure or overgeneralization or other ways in which we gather information and make inferences, but we're not scientific about it, we're not rigorous about it. So, all right, try this one on for size. I apologize in advance if any of this is triggering for anybody, but the observed empirical outcome of standardized math and engineering tests is that males perform better on standardized math and engineering tests than do females. That is objectively true. Like, you can look at the scores and do a difference test, and biologically or male identifying folks perform better on those tests. Let's say 3% better on average, 5% better, whatever. That's a real thing. So the question is, why? The experiment, as is posed here, is what is the proportional effect of sex or gender on standardized math tests or standardized engineering tests? And the unremarkable result was that males perform, let's say, I'm making up the number, 5% better. And so the interesting, that's weird part comes in asking the why, asking the explanatory question of, we got the descriptive result, but was this conclusion premature closure or overgeneralization or some other confounding factor that's only confounding because we haven't thought of it yet? So what do you think the underlying reason might be for this? Is it that men are genuinely better, like genetically, than women at math?
Is it because there's more of like a male-dominated field, so there would be more men scoring on tests than females?
Yeah, that's exactly it. There's a cultural emphasis. Boys are steered more towards math and science and engineering and STEM fields than women are, historically. Now, when you look at other statistics of early career performance and like college level and grad school level performance, women are blowing men out of the water. Just like it's a bad century to be a guy, like really bad. So it's not that males are somehow biologically better at math, it's that they're encouraged to do that. And in some cultures, women are very strongly discouraged, like violently discouraged. In parts of sub-Saharan Africa, girls can be kidnapped and sold off for going to school, like elementary school. Like this is a thing that real people have to deal with like these days, and so forth. All right, so we do a wildlife study with collar tracking, not on rabbits, but on the rare Saluki leopard. So rare you hadn't even heard of it before. And we find that its home range is upland pine in southern Illinois. Upland pine, dry, sunny pine spots. So that was the conclusion. We looked in a bunch of upland pine and we found signs of the rare Saluki leopard. So we looked in upland pine and we found signs of rare Saluki leopard, and we concluded that the rare Saluki leopard's home range is upland pine. What's the premature closure or confounding factor or overgeneralization that is embedded in the conclusion, the research conclusion that is supported by the data, that the rare Saluki leopard's home range is upland pine? What's the problem? Or what could be a problem with that based on looking in upland pine for the rare Saluki leopard?
Are the signs maybe not exclusive to that?
Yes, exactly. They're also everywhere else. Large felids, like mountain lions and stuff like that, can have home ranges or migration routes of hundreds of miles, like all of the habitats in between. But we looked in upland pine, and that's where we found it, so we could prematurely close our search for information and say, okay, upland pine is causal of the presence of the rare Saluki leopard, when that's not the case at all. So think about the scope of your research. Is it wide enough? Are you capturing everything that you need to? Now, in carefully controlled watershed studies, the answer is usually yes. Like, you need to delimit down, actually, very aggressively to specific watersheds. But for a wildlife type study, there is definitely a where am I looking, when am I looking, how hard am I looking? So sampling effort is this technical term there. In terms of premature closure. So you have to be very, very careful in the conclusions that you draw, that they're not overgeneralized or prematurely closed off. Okay. How about this? For undergraduates, more studying results in better grades. Potential confounding factors? What else could lead to better grades? Is a way to ask about confounding factors instead of just more studying.
Doing the homework.
Doing the homework. What else?
Specific classes? Or
The classes that you've taken before this one. I was talking with a young lady yesterday afternoon who is taking, may God have mercy on her soul, she's taking business calculus and has never even taken pre-calculus before. And she's a straight A student, and she's getting just above 50% in this class, and she is going to hard fail this class. Like, she is going to be this class is going to be a crater on her GPA, like a smoking hole. But it's not for lack of studying. It's for lack of correct background. Like, she got dropped in the deep end of the pool without knowing how to swim on calculus. And yeah, there are good resources, and she's going to have a hard semester to try and pull things back together, but it's not going to happen. Like, you can't pick up 2, 3, 4 classes of background in calculus and just, like, make that up while you're taking the calculus class. Also, things like parents' socioeconomic status. Like, were your parents able to afford after-school tutors for you in subjects that you struggled in as a kid? Or were they able to provide for you remedial or accelerated, like pull-out classes in your elementary school, like extended learning opportunities and so forth? So there's a lot of things that go into making better grades, and somebody who just asks questions about how much did you study, how do you study, they're going to miss a whole lot of things, and so their statistics are going to be real low power because there are a whole bunch of other meaningful, important, contributory or necessary or sufficient factors, like we were talking about on Tuesday, that influence that. All right, how about this one? This is a physics question. The Colorado Rockies score more home runs at home in their stadium. So, why do you think that could be?
That's where they practice a lot.
So there might be a home court advantage effect. Might be where they practice, okay? Everybody else also scores more runs there too. As another data point, what could be going on there? Other teams don't get to practice there, so there is nuance here. And this is scary and intimidating when you're a grad student and you're confronting this kind of a question out of your own data, because it's like, oh, there's something going on. I mean, it could be a million different things, but it's okay. You just take a breath, you step back for a minute, and then start thinking, what could it be? It's not space aliens. It's something reasonable and rational, and we can probably figure it out and maybe correct our statistics, maybe not, but at least we'll have some sense of what's really going on here. Sorry, you were saying?
Less gravity.
Less gravity.
I was gonna say something with the atmosphere.
Yes.
Something for how high
Also
it
true.
is.
That's literally it. The mile-high city, right? The air's less dense. There's less friction. The whole reason that airplanes cruise at 35,000 feet altitude into the stratosphere is because there's less friction and air resistance, so you're basically a rocket that blasts off. You use 90% of your fuel in the first 3 minutes of the flight, and then you just glide on through the thin atmosphere all the way to your target. Same thing with baseballs. It's just easier to hit one out the park, even if the park is the same size, and even if the differential effect of microgravity change is really pretty small, there's a huge effect just on friction. Like that is enough by itself. This is the reason that golf balls have dimples, right? Managing air friction. Okay, or drag. How about this? Sugar maples are sap productive in February.
Aren't all trees sap productive?
You got it. All trees are, yeah. But if you're only looking at maples, right? If you're a grad student and your advisor is a world-class expert on maple physiology, it's like, oh yeah, we're really getting into this whole February time frame for this particular regional subvarietal of sugar maple and so forth, and that's not wrong, but it's also pretty incomplete. So whatever these questions are, whatever these sort of latent causal, contributory, sufficient, necessary causes might be in your study, give yourself room to think about that. Is the soil texture really the same across both of your paired watersheds? It's probably close, but is it the same? Maybe, maybe not. So, to the extent that you're assuming those things, you want to be able to trust those assumptions. To the extent that you're still learning to trust any particular set of assumptions that may or may not hold true, get out there and, do some soil texture studies and stuff like that. Just real quick, even informally, you can see, yeah, this is pretty much the same left hand, right hand, left watershed, right watershed. Or it's like, oh man, this is super sandy and this is very clayey. Okay, I need to pay attention to this. I need to factor this into my study. It's not just fertilizer, it's also soil texture plus fertilizer. It's also soil texture as an independent factor, not an interaction factor between fertilizer and soils, right? So for each factor you add, you're adding multiple levels of interactions potentially. Okay, cool. So your advisor has done some adjacent studies to what you're working on right now. It's okay. It's always okay to have this conversation of, so what what confounding factors might we be looking at on this particular study that we haven't really talked about yet, and we're all just kind of assuming we all know, but we may not, because maybe, anybody's new to this. That's totally fine. Okay, real quickly. Now we got like 3 minutes. Let's save time as a variable or axis in research for Tuesday. We'll pick it up there. Okay. I'm around for questions. Otherwise, have an awesome weekend. Hopefully, yesterday's exciting but short rain event did not cause additional data collection needs for you guys. I got caught home commuting on my Segway as the storm wall swept through Carbondale.
Oh no!
It was exciting. My wife jumped in the car and came and picked me up like 200 yards from my house. That's love. That's love right there. Man, marry up. I don't know if you're into marriage. Whatever. I'm just saying. Find somebody that you admire. Okay.